ISPs. From the previous section, we haven't discussed about specific community rules that some of the ISPs have applied. So we'll discuss that before continuing with this one. But first, I want to review the agenda for this section. So first, we'll discuss, after discussing the communities, we'll discuss the role of IGPs and IBGP. Aggregation, which is very important for the health of the internet, and we'll discuss that in more detail. Receiving prefixes from peers, customers, and transit providers. Origin validation, or PKI, for security, verifying that the prefix received is originated from the originator, from an authenticated originator. And then we'll discuss about preparing the network and some configuration tips. So before that, I'll review some of the ISP community rules, what types of rules they use. Here's an example for Sprint. So in this case, Sprint uses different AS numbers, the first using the 6500 range to influence, so that the customers can tell Sprint how many ASs Sprint can prepend to the AS paths. So if a customer wants Sprint to prepend, for example, 4 ASNs, then they will use 65004 to a specific ASN. So traffic or routes advertised to a specific ASN, if it is prepended with 65004, then it will be advertised with 4 ASNs prepended. And then for different regions, it has different values. So here's another example from NTT. In this case, NTT uses different communities for customers to influence what type of local preference to set. So if NTT receives a specific community, in this case, for example, the first one, 9914:450, it will set a local preference of 96. If it is 460, it will set a local preference of 98, and so on. So customers can tell their service providers based on the agreement how to manipulate their attributes or their local preferences based on the community settings that they set. Here is another example also from Verizon. So also here for different purposes, 702.80 will be to set the local preference to 80, 702.120, local preference 120, and so on. Here are some more examples. They are more or less the same. So here is another one for BT. 5400:1000 implies all peers and transits. 5400:1500 signifies all transits. 5400:1501 signifies transiting through Sprint, and another one, 1502, transiting through service, and so on. So this is how they communicate to their transit receivers what those prefixes are. So the prefixes that they advertise to those transit receivers. So here is another one for layer 3, so you can review it. But you can go to each of these websites and to other service providers and see how they use communities to communicate routing attribute decisions between the service provider and their partners, peers, customers, and transit receivers. Okay, getting back to the main session. Here first we'll discuss the role of IGPs and IBGPs, when to use each one of them and when not to use. the importance of aggregation, receiving prefixes from different entities, using origin validation to make sure that the route received from a specific origin is really an authenticated origin. And we'll see the reason why that's important, preparing the network and configuration tips. So the role of IGPs and IBGP. So first, let's discuss BGP versus OSPF, ISIS. OSPF and ISIS are the main IGP protocols used in service providers. So the IGPs, ISIS and OSPF, they are used to carry infrastructure addresses, like interface addresses, loopback IP addresses, and so on within the service provider network. They are not used to carry customer addresses. And they are not used to carry, obviously, other service provider prefixes. So the design goal is to minimize the load on IGP so that IGP converges faster. Because BGP recurses into IGP, so it depends on IGP. So a fast converging IGP is also important for BGP convergence. So internally, you can use BGP using obviously IBGP, and then externally using eBGP. So IBGP for internal use is used to carry customer prefixes. Also some internal prefixes, particularly towards the edge. For edge devices, instead of carrying them in IGP, you can carry them in BGP, in IBGP. But the prefixes that you carry in IBGP does not necessarily go to your eBGP updates, and usually they don't, and we'll discuss that also. So eBGP is used to exchange prefixes with other ASs, and you also apply routing policy there. So again, to review the model, you have IGP and IBGP within a network, and then eBGP between networks. Very important to note here, it's very important not to distribute BGP into IGP, also not to distribute IGP into BGP. Do not use also IGP to carry customer prefixes. It's very important to inject customer prefix into BGP because you want to reduce the size of your IGP so that IGP converges faster. So these are very important. So how do we inject routes into BGP? And we'll discuss that later on. But it's not by distributing IGP into BGP. You have to inject specific prefixes using network statements and static routes instead of just distributing routes. So again, use IBGP to carry customer prefixes of that ISP essentially. You can point a static route to the customer interface, or you may even, depending on scenario, you may even create a floating static point, static route that will not go our way. Even if the customer interface goes down, you don't want that to propagate to the rest of the network. Obviously, you don't redistribute customer prefixes directly to your eBGP peers. You only use this for your internal routing purpose, for your internal table. So if you want to inject routes, customer routes as well as your own route into BGP, you can use network segments as well. But when you redistribute into your eBGP, you have to make sure that you are advertising on aggregate prefixes. You don't want to advertise specific prefixes. For customers, typically you don't run BGP with your customers. But if you have a big customer that's peering with you at multiple locations, or that's connected with your network at multiple locations, it's important to have some kind of routing protocol, and BGP is a better better than other protocols for that purpose. So in that case, it's good to use BGP with the customer, exchange routes with using BGP with the customer. So there are two scenarios. It's possible that the prefixes are from your own prefixes. So you assign those prefixes to the customer. Even in that case, it's important to exchange routes with the customer if you are peering at multiple locations, or connect if the customer is connected at multiple locations. The other scenario is if the customer is peering not just with you, but with other service providers, and if it has its own address space, it's important to exchange those routes as well. So, but in that case, those routes, those prefixes are assigned directly to that service, to that customer. You don't want to advertise a prefix assigned to that customer from another service provider to another service provider. You only advertise or receive advertisements, prefixes assigned to that service, to that customer, either from your address space or directly to the customer from a registry. Okay, so aggregation. So if you notice the question here, quality or quantity, when you aggregate, you are reducing the size of your routing table and improving the quality of the internet in general, and we'll see the reason why. When you advertise specific routes, you are increasing the size of the internet table. You may achieve some level of traffic engineering, but there are other ways to achieve that. So it's not really good or advisable to send specific routes that are not aggregated from customers to the rest of the network. So aggregation is very important. So aggregation means basically advertising blocks received directly from registry or received through the standard class-based allocation, which is rare, right? So sub-prefixes of the registry assigned addresses can be advertised to some service providers for traffic engineering purpose, but it shouldn't be propagated to the rest of the internet. So it should be advertised to some service providers by agreement, and then it's important that those service providers do not subsequently advertise to other service providers. Only the aggregate should be advertised. Again, this is important for the stability of the whole internet. But as you will see some of the numbers, a lot of people advertise more specific prefixes than the registry entries. So the registries are normally /22 and lower, but you will see a lot of /24s on the internet. Again, sub-prefixes should not be advertised to the rest of the network. They may be advertised to some service providers for traffic engineering purpose. And usually, we'll see there are some tools and websites that are tracking the prefixes, and some of the service providers who are not complying are normally regarded poorly by the community. And you will see some of those, and you can see the reports for yourself. Registries publish their minimum allocation size, and it ranges from /22 to /22. In some cases, there are /24s because we are running out of address space, the IPv4 address space. Here is a bad example. Let's say AS100 has a customer, has assigned IP address from its own address space to the customer, which is a /23. So it has a /19 assigned from the registry, and it has assigned /23 to one of its customers. So if it advertises that /23 to the rest of the internet, that's really a bad example and creates a problem. So why? Suppose the customer link goes down. What happens? When the customer link goes down, that route will be withdrawn from the service provider. And the service provider will withdraw that from the rest of the internet, and that will propagate throughout the internet. And when the link comes back later on, the service provider advertises that route, sorry, the customer advertises that route to the service provider, and then the service provider advertises that route again to the rest of the internet, and then second time causes another churn to the internet. So when that adds up from multiple service providers, it creates a lot of churn to the internet. So that's the reason, that's one of the reasons why it's important not to advertise the customer prefix that you assign to the customer to the rest of the internet. You can just assign the /19 only to the rest of the internet, but in some cases maybe just maybe /20s for traffic engineering purpose, but it's not really important, necessary to advertise the customer as a prefix to the rest of the internet. Here is a good example. Again, the AS100 has assigned /23, but it's only advertising /19. So when the route goes down, when the customer /19 route goes down or the interface goes down, the route is withdrawn from the AS100, the service provider, but nothing happens to the rest of the internet. The impact is only to that network. So if you think about it, even for the customer, in the previous case, for the customer to receive traffic from the rest of the network, that prefix has to propagate throughout the network before it receives traffic for that prefix. But in this case, since nothing is going to the internet and traffic is coming to that prefix anyways, since traffic is coming to that prefix and getting dropped at the upstream ISP, which is ISP 100, when the traffic is advertised, the customer will receive traffic quickly. So it's good for the customer, it's good for the rest of the internet. So good example is what everyone should do, but for different reasons, that doesn't happen. And normally it is for lack of understanding of how the impact and the value, and in some cases just disregard for poor knowledge, essentially. So another very important thing is it's very important to separate routes with an IBGP and routes that are sent across eBGP. Routes that remain with an IBGP includes customer prefixes. Some of the infrastructures even that are not in the core are in IBGP. But you don't advertise those to eBGP. You only advertise the aggregate address space. And you don't want to do traffic engineering based on a customer prefix. If you want to do traffic engineering, the ISP should create other sub-prefixes and then split them across multiple service providers or upstream providers instead of using directly the customer prefix. By doing that, it is making the network stable because those prefixes will remain active because they are being advertised from multiple points. So here is from a year ago. So the BGP table says we'll see some of the today's numbers later on. It's about 45,000, 450,000 plus on the internet. But a year ago it was 420,000 internet routing table. And if you do CIDR aggregation based on CIDR address space, you can reduce it to 243. If it is aggregated using a maximum aggregation mechanism, it can even go down to 181,000. So you can see that the current table can easily be aggregated to be more efficient, which is either 250 or 180,000, but it was 420,000 last year. So the same proportion pretty much remains the same this year. This year it's around 450,000. But what this shows you is a number of service providers are not really aggregating based on the CIDR or the registry size. And as you can see, there are some other spaces that are producing a lot of prefixes. So if you look at this table, this is from 1999. In 1999, the 24/8 and some of the 192/8, particularly the 192/8, was the one that was generating a lot of the prefixes, which was 6,000 per /8. But in 2010, that has changed significantly, and 64/8, 66/8, and 74/8, and so on. The ones that are highlighted are generating a lot more prefixes per /8. So these are, they are called the new swamps. So the 120 RIRs combined, if they generate 5,000 prefixes per /8, will increase the routing, the internet routing table to over 635,000. If that number goes to 6,000 per /8, as per the trend, the internet routing table may go to 762,000, and so on. So why is a new swamp? So some of the reasons are lack of knowledge. In some cases, just not being, laziness, essentially. In some cases, they know it, but they think it is necessary and they do it. So efforts to improve. There was some initiative that was done early on, started by Tony and then revised by Philip Smith. And Philip Smith used to deliver this presentation, actually, and now combined with Geoff Houston. There's a CIDR report. You can go there and check the different reports, and we'll see some of them here. So it computes the size of the routing table, assuming ISPs perform optimal aggregation, and compares it to what it is without that optimal aggregation. So if we look at the next table here, this is from yesterday, or it's from yesterday. So you can see that, so it's not fully visible, but you can see that the prefixes, current prefixes, total prefix on the internet are 457,000 plus. But if they were CIDR aggregated, they would have been reduced to 261,000. Okay. So in summary, there are 44,000 ASs in the routing system, but only 18,000 of them announce one prefix. The rest announce multiple prefixes to the internet. And 3,000 is the largest number of prefixes announced by a single AS, and that's Bell South. And you will see that report on the next one. So here is a ranking of basically who is advertising more prefixes to the internet. And as you can see, it's Bell South, and it was Bell South last year also. It's Bell South advertising 3,000, and the next one is net services for 2,700 and so on. You can see the ranking. So you can see this ranking for any day. So this is per origin S. The previous one was what was announced. Again, also per origin S, Bell South is the largest. And then who is advertising more specific prefixes than what is provided to them. And you can see it is still Bell South, but the others change a little bit. And here, here is some aggregation suggestion. So based on the analysis, the tool does the analysis and then suggests what should be added and what should be removed. So the red ones are what is suggested to be removed, and the green ones, the aggregate prefix. So the tool does really a good job of analyzing it and suggesting aggregation alternatives. So importance of size of routing table. So it's very important to understand that today memory is not an issue. So you can really have millions of routes. Most of the routers that are available today, they can do millions of routes. So that's not the main issue. Even CPU has also increased significantly. There's a lot of CPU. But at the same time, there is a significant expectation that BGP should converge faster than it used to. So if you want to converge BGP faster with large number of routes, even if you have large memory, so the memory doesn't really influence the convergence, it's the CPU. So the size is not really because of the memory issue, it's mostly because of the convergence issue. The expectation is BGP needs to converge faster because there are lots of applications that depend heavily on the convergence of the network in general. So it's important that BGP converges faster, and to do that, you have two things to play with. One, you can reduce the size of the BGP table, and second one is you can increase CPU. And obviously, CPU has been increasing, but at the same time, the expectation of convergence has been also getting higher, but the size of the BGP table has been increasing. So it's important still to make sure that people follow the guidelines and reduce the BGP table size so that the internet converges faster. And here is another report, BGP instability report. This shows you for the past 7 days the most active ASs. So you can see in this case, so this is the past 7 days, so it doesn't mean that this is always the case. Maybe there is some specific event that caused this problem, but you can see that ASN 36998, which is SDN Mobitel, has been very active for the past 7 days, and with 9.69% of the impact essentially, and followed by others. But it's a really nice report that you can see all this. Again, 50 most active past 7 days. This is another past 7 days. Here is another also report. The URL is also shown there. Here, what this shows is the green line shows you the BGP table over time, and you can see that today it is over 450,000. The next line, which is the purple line, shows you what it would be if it is aggregated based on the AS paths. If you aggregate prefixes based on identical AS paths, you can reduce it by almost to almost 250,000. if you use AS origin instead of AS paths for aggregation, you can even further reduce it below 200,000. So there's a lot of room to play with to reduce the size of the BGP table on the internet if people comply with some of the suggestions. So in summary, the aggregation could be much better. It's possible to get 35% saving if the recommendations are implemented. A lot of people are implementing them, but some are not. So it's just the summary report pushes people to be more conforming than violating some of those rules. Any questions on aggregation? So receiving prefixes. So a service provider may receive prefixes from a customer, from a peer, or from a transit provider or upstream transit provider. So we'll see each one of them. From a customer, ISP should not accept prefixes which have been assigned to the customer by another ISP. If the customer has prefixes that are assigned by another ISP, this ISP should not advertise those prefixes to the rest of the internet, should not even receive them from the customer. But if the ISP has assigned those prefixes to the customer, then the customer can advertise them, and it's useful particularly if the customer is connected to the service provider at multiple points. And it gives you redundancy as well as load balancing. Also, if the customer has received an assigned IP address or IP address block from a registry, then the customer can advertise it to multiple service providers because it is explicitly assigned to that ISP, to that customer, and it also has its own AS number. You can check who owns a specific prefix using the whois tool, basically. Here is one example. In this particular example, it's checking the prefix 202.12.20.90 on the ethnic database registry, and it shows that it's assigned and it's portable, which means it can be used. And here, in this case, you can see that it is allocated unspecified. So this is basically assigned by from the service provider address space. So basically, you can use whois to check whether a specific prefix has been assigned to a customer. If the customer says, I have an IP address that I received from a registry, it's important to check it. What about from a peer? From a peer, it depends on the agreement. Usually there is a bilateral agreement between peers, or there may be some, in the public peering scenario, there will be some, you have to verify that the prefix is assigned to that service provider or to its customers before you can exchange those prefixes typically. So, so when you get into an agreement, you can exchange emails and document them. You can also check the registry to see if those addresses have been assigned to that ISP or to its customers. You can also use, this is a new mechanism, use origin AS validation, which we'll discuss later on. From upstream service providers, usually you have few alternatives. If you are peering with multiple service, getting transits from multiple service providers, you can receive the full table from each one of them. Usually that's costly. If you are receiving, if you are just using one transit provider, you may just point a default route to that service provider or receive a default route from that service provider. In some cases, you may receive partial routes. If you are peering with a service provider at multiple locations, and if it's just one service provider, you can use partial, which means you can use the routes from the internal network of the service provider, but the rest of the internet you will use default. So default plus partial. So 3 scenarios. You will either point a default or receive default plus partial, or receive full table, particularly if you are peering with multiple transit providers. Again, when you receive routes from transit providers, it's important to make sure that you do a filtering. You make sure that you are not receiving private IP addresses. Make sure you are not receiving bogons that are maintained by Team Cymrus. Make sure that for IPv6, also make sure that those prefixes are not in that list shown there. And Team Cymrus regularly publishes bogon prefixes, so it's important to implement bogon filters to filter those bogon prefixes. You can also receive bogon advertisements from Team Cymrus to make it dynamic instead of waiting for, instead of checking the bogon table frequently. Okay. So in summary, it's important to pay attention what types of prefixes you are receiving from your customers, your peers, as well as from transit providers. It's important for the integrity of your own network, as well as for the integrity of the internet. Any questions? So we'll discuss some of the issues involved with receiving prefixes and advertising prefixes. We'll see some specific cases where it caused a significant outage to the internet, and how we can use origin validation to fix that problem. I'll go specifically to this example. So this is well documented example, and we'll see the specific case. Take the following scenario. Let's say there's a client there, and two ASs, AS20 and AS40 advertise the same prefix. Let's say that AS belongs to AS20, legitimately belongs to AS20, sorry, AS40. But both AS20 and AS40 advertise the same prefix. By default, because AS20 is a shorter path, AS20 will be picked. So unless there is a mechanism to verify that AS20 owns that prefix and make sure that AS10 blocks that prefix received from AS20, then traffic coming from the client to that prefix will go through AS20 and may be blocked or dropped somewhere. So this is one case. Here is another case. Even for the same, even if the AS path is shorter, if somebody advertises a more specific route of that prefix, then traffic will go to the more specific route, even if that path is longer path. And traffic will be black-holed because of that. There was one such case a few years back, I think about 3 years ago. What happened was Pakistan Telecom advertised YouTube's prefix, a more specific version of YouTube's prefix to the internet. So they didn't do it intentionally. I think there was some request from the government that they block YouTube because of some cultural reasons. And to do that, they went this way, obviously lack of technical knowledge on the people who did that. And by doing that, what happened was any prefix that was going to YouTube ended up going to Pakistan Telecom. So obviously it's not good for Pakistan because it will overwhelm their network, and it was not good for YouTube because nobody was able to access YouTube service for, I think, for part of a day or for a full day. And that was because Pakistan Telecom advertised a more specific version of a YouTube prefix. In this case, they advertised /24 of this, but YouTube was advertising /22 because YouTube was being good for the internet and advertising only the prefix, the /22 prefix, to make internet stable, but Pakistan Telecom was advertising more specific, so attracting the whole table, the whole traffic to them. So question is, how do you prevent that? So as a result of that and other incidents, they started working, the security internet domain routing working group within IETF started working on the origin AS validation. And you'll see those, and then if you go to the working group, you will see a lot of drafts and RFCs associated with origin validation and RPKI. RPKI refers to the resource public key infrastructure that's used to do origin validation. And in summary, here is what it looks like. So there is a remote distributed RPKI repository that stores the legitimate owner of each prefix. So the origin AS of each prefix, and through RPKI cache, a service provider can receive the RPKI cache information from the cache servers. It is not a BGP protocol, it's a different protocol, but nowadays, I believe at least a couple of vendors have already implemented it, including Cisco and Juniper, but I'm sure others have already started implementing it. So what you do is you receive this from the registries, and then when you receive a route from a service provider or a peer, you can check it against the database automatically. And then it will classify the validity status. So here is an example. Let's say the registry database has what we call ROA. ROAs on the right side. And let's say you receive from your peer or from your eBGP peer those prefixes on the left side. So the first one is in the registry and it matches. That is, the origin AS number matches the origin AS number in the registry, in the cache. So it's considered to be valid. Okay? In the second case, there is no matching. In the second case, there is no matching prefix. 10.01/24. Oh, there is a matching. There is a matching prefix, which is 10.0/16/24. There is a matching prefix, but the origin AS is different. The origin AS in this case is 200, and in some cases 300, but the origin AS received is 400. So in this case, it is invalid. So that AS is not allowed to originate that prefix. So it's not a legitimate originator. The third case is there is no match. So it's not in the registry. So in this case, it's considered as unknown. So what happens is, as this table is being built, some of the routes may not be in the registry for some of the service providers. In that case, it will be in an unknown state. From a preference perspective, obviously, you prefer valid, and then unknown, then invalid is the last one. And normally, after that, you can apply policy. So this is a classification, and then BGP is policy oriented. Then you can apply policy. You can say, if it is invalid, block it, drop it, or prefer it less. If it is unknown, prefer it less. Something like that. But you can apply policies to influence the decision. But the job of the RPKI system, or the origin validation system, origin-based validation system, is to validate the origin. So once the validation has happened, the border router can notify other routers through a new extended community about the state of the origin validation, either invalid, unknown, or valid. And then other routers can decide what to do with that, based on policy, obviously. Question on origin validation? Okay. So the next one is just how to implement or roll out BGP in your network. So you will need ASA number, obviously. If you want to deploy BGP, you need autonomous system number. If you are multi-homing to multiple ISPs, you will need a public autonomous system number. If you are just peering with one ISP, you can use a private ASA number. Obviously, you have to agree, right? If you are going to peer with multiple service providers, then you need to get your own assigned IP address from the registry, if you can get it, right? So it's running short, right? Or you can get, if you are just peering with one ISP at multiple locations, then you can get it from that ISP. So the assumption is there is no BGP running and there is no IGP running. So it's just a new network starting, essentially. So first you have to decide what type of IGP protocol to run, OSPF or ISIS. Both of them are link state. Depending on, it may end up being, the decision may be, which protocol do I feel comfortable with, or which protocol do I know most, or my team knows the most, and you will go with that one, typically. Some people prefer ISI, some people prefer OSPF, so that's a different set of questions, but typically you will pick one of them. Then obviously you have to have loopback IP addresses configured. Obviously the loopback IP address will be /32, and they have to be injected into IGP. And then you'll start, it's used for BGP peering as well as for route origination. That's the loopback IP address. It's also used for router ID for BGP. If you have a network that has static routes, you can deploy IGP without impacting your network, because in most cases, static route has higher preference over IGP. So by employing, by adding IGP, you are not really changing the routing within your network. But once you deploy IGP and make sure that the IGP is working properly, you can start removing the static routes and then make that your whole network is running IGP. So it's very important that your link state database is lean. So you don't want to inject BGP into your IGP or inject your customer networks into IGP. That will make your IGP large and reduce your convergence time for IGP. And convergence time of IGP is very, very important. Okay. if you have routes that do not go into IGP, for example, if you have customers that are being aggregated through DSL, or you have customers that you have assigned IP address from your address space, then you can inject those prefixes into IBGP. You don't need to put them in IGP. And also the interface address from your router to your customer, you don't need to inject it into IGP. You can put them in BGP. Okay. The second stage is once you have your IGP, second stage is to build your IBGP. Obviously, if you have a small network, you can do a full mesh IBGP. If you anticipate large network, or if you have a large network, then you have to do either confederation or route reflector. Obviously, route reflector is better if you are starting fresh. So you will have to pick a couple of routers as route reflectors, or if it is very large network, then you may split into multiple zones, and each one of them will have a couple of route reflectors for redundancy purpose. So, and IBGP must run on all routers that are potentially used for transit traffic. And transit means transit from a customer to the rest of the internet, or transit from one customer to another, or transit from one service provider to another service provider. So the next phase is build the transit paths. So here, in this particular example, you can see that A and B are obviously transits, but in case the link between A and B goes down, D is also a transit. But C, E, F are not really transit in this case. So which means C, E, F do not really need to get the full internet routing table or the full table. But A, B, D have to have the full internet table if this network is going to become a transit. So typically, if you have a transit, if you are going to become a transit, and in most cases actually, you will have multiple layers. Here is an example: a core, distribution, and aggregation. And typically, the core has to have the full internet table. The aggregation doesn't need to participate in the full IBGP table, but the distribution, depending on the scenario, may or may not participate in full internet table exchange. Again, the key is if in any circumstance any router may become a transit, then that router needs to have the full internet table. So for aggregation layer, IBGP is optional because you can run other protocol or just IGP, and then at the distribution layer you can inject those routes into IBGP, or you can extend your IBGP to aggregation layer and then inject routes there. But it doesn't need to carry the full internet table. It can participate in IBGP and carry only the internal network table, but it doesn't need to carry the full internet table. And actually, most aggregation, a lot of the aggregation devices may not even run BGP, may not even support BGP routing protocol. The distribution layer usually runs IBGP. It may carry the full table, or it may carry just partial, depending on, again, whether there is a possibility that it may become a transit or not. If it is going to become a transit, then it has to carry a full internet table. If there is no reason, if we know that there is no way that the distribution layer will be a transit, then there is no need to carry the full table. Partial will be sufficient. Okay. Again, it doesn't have to run IBGP. In most cases, it will run IBGP. It doesn't have to carry the full internet table. In most cases, it doesn't. But the core has to participate in full BGP, should run IBGP, should carry the full internet table. The core includes the AS border routers as well. So now you have to decide on policy. So do I want to have full internet table everywhere, or partial somewhere and full somewhere, or no IBGP somewhere and full IBGP in some places? So depending on your circumstance, you'll decide that. And obviously you have to implement communities for scaling purpose. Again, if you think that your network is going to grow, or if it is large already, then you have to implement route reflectors. Configuration templates are always important. And configuration templates makes it easier to scale your configuration and also make your system stable. So what you do is, to implement IBGP, you will implement IBGP mesh on select routers. Let's say if you have few route reflectors, you will have IBGP mesh between the route reflectors, and then there will be clients to those route reflectors. Another important thing is you have to make sure that IBGP distance is greater than IGP distance. Distance is a preference in terms of routing protocol, which protocol to be used when deciding that if a prefix is received from two different protocols or multiple protocols, then the distance of the protocol determines which one is the best. The lower distance is preferred. Typically, for example, on a Cisco system, IBGP uses a distance of 200, and IGP is used depending on the IGP. I think for OSP and ISIS, it's about 110, 115. But it is lower than IBGP. Step 2, you will install customer prefixes into BGP and make sure that the network is still working. And you can inject them by pointing a static null to a static route to the customer, or a static null to at the border router, a floating static null. So that's stable. And then, since you already have static routes, initially you have to gradually remove them and make sure that IGP takes care of that. And finally, you will configure eBGP peer with your transit providers, peers, or customers. So now, installing customer prefixes. Again, here is a summary. We have already discussed some of this. If you have a customer assigned address space, you can use a network statement to inject those prefixes. And you can use unique community to make sure that those prefixes are not advertised outside your network. If those prefixes are advertised from your own address space, you don't want to advertise the specific routes to other service providers. The customer-facing point-to-point links, typically you can inject them into BGP, IBGP, and then use Next Hub Self instead of redistributing them into IGP. And if you have pools and local LANs, you can use, again, network statements to assign prefix for those networks. Again, you will carefully remove the static routes, one router at a time. And this is assuming migration from a static route. So if you don't have anything, if you are starting from a scratch, then you don't have static route. You start from IBGP. So in this particular case, we assume that initially there was static route, which is usually very unlikely. But the key here is most of these steps that we have discussed are not flag-based, which means it doesn't really cause disruption. So you can do them step by step at different times, at different maintenance windows. Any questions? Okay. So here we will discuss some configuration tips and summarize some of the discussions we discussed with respect to configuration. So it's very important that we use loopback IP addresses for IBGP peering. Also use the loopback IP address as an X hub using Next hub self instead of using the interface IP address, directly connected interface IP address as an X hub, which is a default behavior. The DMZ networks, that's the networks that connect your network to your peer, either customer or another service provider. You can inject them using IBGP, but if you do that, then you have to use Next hub self. So again, summarizing the Next hub self. By default, BGP speakers announce external networks to IBGP peers without changing the Next hub, which is a directly connected interface or the peering IP address. But that's not recommended. It's better to override that with Next hub self. And this is used by most service providers. Another important consideration, some implementations of BGP do not support AS path lengths beyond a certain number. So it's important that you do not exceed the AS path lengths beyond a certain number. Normally more than 20 is really too much. There are tools, you can use BGP Play to see what's the maximum lengths on the internet, unique lengths. If you do prepend, don't prepend too much because those routers may drop your advertisements. Those routers do not support AS path lengths beyond certain number may drop your routes. So it's important when you do prepend, make sure that you are not prepending too much. So as you can see from a last year report, the average AS path length was 3.8. The maximum AS path length is 13, but with a prepend, there were some AS path lengths that as long as 34. And you can see that that's really bad behavior because the maximum length was 13. So if you exceed 13, that's enough. So the prepend should have just resulted in 14 instead of 34, but because it was not done carefully, it went up to 34. So here is an example of ridiculously long AS path lengths. And in this case, actually it is even unique. It's not even any prepend. The next one is a prepend. Next one is, it has just 3 AS paths unique. The unique AS path length is actually 3. The rest is prepended. The 12 or 26 is prepended so many times. So you can limit the maximum AS path length. Another important aspect, important implementation is generalized TTL security mechanism, GTSM. Formerly it used to be BGP TTL hack, BGP TTL security hack, BTSH. With this, when you establish eBGP session, you can say, I will only accept BGP packets, which are TCP essentially, port 179, only if the TTL is 254 or 255. For that to happen, your peer has to set the TTL to 255. So the advantage of that is if somebody wants to establish a false TCP session, an authorized TCP session from beyond that router, it will not be able to do that because by the time the packet arrives to your router, the TTL has gone below the TTL threshold that you set using the GTSM features. Most of the modern routers have implemented this in hardware, so it's actually filtered in hardware. So that helps you. It doesn't actually penalize your CPU. It's blocked in hardware. If the TTL exceeds 254, it's automatically dropped if you implement this feature. So it's an important security feature. So you can see that a legitimate traffic, it says TTL of 255, so it works fine. But somebody from outside trying to hijack your TCP session, by the time the packet arrives to the router, it's already less than the threshold and it will be dropped. Okay. Templates. Most of the configurations, let's say you have several iBGP peers from a router reflector, most of those configurations are the same. So you can combine the similar configurations into a template and then apply it to individual peers. So that's basically templating. Same thing with the policy, prefix list, and so on. So it's a good practice to use templates for everything, because even if you have just one peer now, you may have multiple peers in the future. So it's better to start from a template, even if you don't need it today. You may need it down the road. And there are some templates, suggested templates, again from Team, I think it is pronounced Kimru, from Team Kimru. And you can look at for different templates for different OSs, router operating systems. And you can apply those, you can use some of those templates. You can use them as a starting point to build your own template. For example, our iBGP templates may contain things like next hub self for all iBGP peers. You can say, do my iBGP session from the loopback IP address. You can also say, send communities. In some cases, you may have to explicitly say BGP version 4, even though almost there is no any other version nowadays. In some cases, it's not even applicable. Like, for example, in Cisco XR, version 4 is the only version supported in XR, so there is no configuration for version 4. But if you have that option, set it explicitly. You can use MD5 password, password for your session to make it secure, or in addition to the TTL hack mechanism or the GTSM mechanism. You can apply things like remove private ASs. It's very important to do that when you receive updates from your, or when you send updates to your eBGP peers. It's important to remove them. Also, when you receive, it's important to remove them. So it's good to have multiple layers of security, not just one. So it's good to have a backup. If you use prefix-based filter, you can use also community-based filter, just a backup to make sure that if there's a mistake in one, it will not impact, it will not have effects. Another one is you can limit the number of routes received from a peer, or the total number of routes received by the router. And you can set it such that you receive warning, or you can set it such that you reset the session. You can again limit the maximum AS path lengths received. It's important to log changes of neighbor state. So if you configure that, then whenever the neighbor goes up and down, it will be a syslog will be generated and it will be in syslog, and it helps you in troubleshooting any potential problem. Again, in summary, use configuration templates. Standardize the configurations across all your routers. You can start from the configuration template from Team Kimru. Use standard, use the TTL security mechanisms. And the templates usually help you reduce the overall load in terms of configuration. So it helps you scale. Okay, with that, the session is concluded. So we have plenty of time. So it would be good if you have questions. Yeah.
For the regional network for the state of Louisiana, higher ed, I'm wondering what you recommend for logging BGP prefixes and changes.
You mean changes in BGP?
Like a historical, we demoed a product by Packet Design called Route Explorer. It's an excellent product, but it's just way too expensive. And we've had trouble finding a solution that may work that's a little more affordable for higher ed.
Yeah, I'm not, unfortunately, I'm not aware of some of those tools. Most of the routers do not support that type of feature, but obviously you can have a tool that will be, let's say, a client of a route reflector and receive those updates. But I'm not aware of the tools.
Can I ask another question?
Sure.
RPKI, I'm wondering, we've got a scenario where we do a peering with LSU, their AS 2055. They're advertising us a bunch of prefixes they own in V4 and V6.
Okay.
And in a situation for their dorms, we do a private BGP AS with them, okay, where we've allocated them our V4 space, so it works fine, but they're advertising us their own V6 space. And I'm just wondering with RPKI, if it's doing that sanity check to see who owns that prefix, is that going to break their V6, you know, when we advertise it out?
Yeah, either you have to disable RPKI checking with them, otherwise they have to use their assigned AS number for RPKI to work.
Randy Bush, Dragon Labs. No, they don't. You, whoever he is, where is he hiding? Ah, there you are. You have a separate trust anchor and have under that trust anchor a certificate for the AS and for the prefix that you're talking about, and undoubtedly you have many of these cases, and ROAs for them, and then your routers will properly validate that. Okay? There are even further, more Baroque cases where what you want is to edit the structure. The whole game of the RPKI is the power is with the relying party, you who are running the routers, the operator. And so there's even further something, a draft that's out there, and there's 1.5 implementations called local trust anchor, where you can actually remove things from the public tree and substitute your own. People doing complex private arrangements would use this. There are governments who like to edit the internet even more than ours does, to whom this appeals, etc. Thanks.
Thanks, Randy. Questions? All right, thanks. I'll be here if you have more questions.